Hello students, in the series of video lectures on VLSI technology, subject code KEC 053, here is a lecture 2 based on crystal growth. Prior to that, in the first lecture we have seen introduction to IC manufacturing, the requirements of IC industry and why silicon is being the preferred material. I am again your faculty Sangeeta Mangesh from Department of Electronics and Communication Engineering, JSS Academy of Technical Education, Noida. Going ahead with this particular lecture, we are going to study first the crystal growth, that is how the first stage of crystal growth starts with obtaining metal grade silicon, followed by obtaining electron grade silicon. Finally, we will see the actual crystal growing techniques, and lastly we will compare these two techniques to find out their plus and minus points. The learning objectives are describing the process of silicon growth, which starts with MSG and electron grade silicon preparation, and basically finally you will be able to compare both the crystal growth processes, that is Czochralski crystal growth process and float zone process. So, comparison of both the processes which are available for silicon growth. So, how the growth process starts? It starts with single crystal silicon getting formed, followed by shaping of those, then wafer slicing, then starts the edge cutting, like you will cut the edges for identification marks, then you will etch, polish those to the mirror polishing process, like you will make the wafers as shining as your mirror. Then at every stage you have something known as cleaning process, then you have inspection of those wafers, and finally you will go for packaging. So, these are all stages or these are all steps which are involved. Out of all these steps, in this lecture we are going to first focus on the first stage, that is the crystal growth, where we are going to have a single crystal being grown right from the sand. So, how that is being done? So, under stage 1, that is obtaining sand. This sand is obtained from the clean beaches of Australia, and it is basically from the earth's crust. Whatever sand you obtain, that is combined with coke and coal, and then in this submerged arc furnace it is heated up to 1600 degrees centigrade. Now, what happens? It is a very thermally extensive process where lot of energy is getting generated, and the energy is approximately 13 kilowatt hours per kg. The temperature of that sub-arc furnace is around 1600 degrees centigrade, and here we are having the silicon mixed with coke and coal getting converted or with combining with silicon dioxide, giving us silicon in liquid form, SiO2 in gaseous form, and carbon monoxide in gaseous form. So, here we are having in liquid form this metal grade silicon. So, we are able to obtain metal grade silicon. Now, this metal grade silicon has got lot of impurities into it, and therefore, we combine it or we carry out pulverization with this silicon to react with anhydrous hydrogen. Now, what happens in this reaction? A trichlorosilane is formed, which is the most recommended material and stable material which is widely used for preparing silicon wafer. Now, what is the reaction happening? This silicon, which is metal grade silicon, reacts with anhydrous hydrogen and gives us trichlorosilane, and these are the byproducts which are released in the form of gases. The trichlorosilane is then purified to obtain silicon, and this silicon has got comparatively less impurity. The impurities are to some extent, that is part per billion per billion form में you will have some metallic impurities, oxygen and carbon impurities, which can be manageable one. Another property of this raw polycrystalline silicon, what we obtain is, it is a polycrystalline material in the form of rods. Now, this is the structure in which this material is available. Now, what is being done is, these materials are further, okay, there is another process also. From trichlorosilane we can have pyrolysis being carried out at 900 degrees centigrade, and we can obtain this same polycrystalline silicon, which is in the form of rods. Now, this polycrystalline silicon has the base material, it is basically is the base material which is used for preparing single crystal silicon. The advantage of this pyrolysis process is, the byproducts are can be easily disposed, and you have the cost effectiveness of this particular process, because it is less expensive, and the overall worldwide consumption of such particular, since silicon is so large. So, we prefer economical process, and therefore, pyrolysis is preferred. These crystalline multicrystalline polycrystalline silicon rods are then crushed, and subsequently we go for the production of other processes or other things which are known as, okay. So, these are high purity polycrystalline rods, and these rods can have impurities such as arsenic, boron, phosphorus and antimony. It is melted at 1400 degrees centigrade in the quartz crucible. So, molten impurities, those are still existing, they will be slowly getting deposited in the molten silicon, and slowly the single growth silicon wafer or single crystal silicon wafer will be grown. The process is called silicon growth, because from the single crystal or from the molten substrate you are having a crystal getting grown or getting developed, and this is the furnace which is known as Joukrawski furnace, which is basically used for this particular purpose. Now, there are 4 factors, please remember, there are 4 factors which are governing the entire design, and those 4 factors we are going to see subsequently, but this is the main process which is adopted or which is widely used, globally used for preparation of pure single crystal silicon or monocrystal silicon. Now, it is somewhat similar to what we used to have Buddi ka ball in the earlier days, or we were young. You know already, in that Buddi ka ball also, that person used to have sugar syrup and used to dip one stick and then rotate that stick, and used to have this strand of sugar getting deposited on that wafer, and we used to have that Buddi ka ball getting created. So, this is somewhat similar to that. You are having a molten silicon, in this you are having the this particular dopant inside, and this dopant will be creating, or this particular thing will be giving you the flexibility to go ahead with the, okay. This will give you the flexibility to design the or develop or grow the silicon, molten silicon will be solidified and the crystal growth will happen. Now, the important aspects what we need to study in this case is, very first thing is the crucible. Since the molten silicon is having very high temperature, that is higher than 1400 degrees centigrade, the material which is to be used for crucible has to be chemically inert. That means, the material should not release any impurity into the molten silicon at that high temperature. Secondly, it should be, the height and diameter also should be good, and that is how it is theoretically proven. There are a lot of calculations going into the dimension design, and the proposed design what is being largely used is containing approximately 60 kg of silicon, molten silicon, and the height is 45 centimeter, and the wall thickness is around 0.25 centimeter. The susceptor which is holding the silicon, now this was about the furnace, and this is the susceptor which is holding the silicon. The susceptor which is holding the silicon, the susceptor also should provide a stable support to the crucible which is holding 60 kg of molten silicon on top of it. Thirdly, the chamber in which this entire molten silicon is present, the chamber should be chemically inert, because any impurity can contaminate the molten silicon. As it is at high temperature, and the reactivity at high temperature can further contaminate the molten silicon and can same impurity can get introduced into the single crystal what is being grown. And lastly, the power supply, which is basically provided by the resistive heating. So, this is about the furnace as far as design of furnace is considered. The second aspect of design considers the crystal pooling mechanism of this particular CZ process. In this CZ process, the seed crystal what you are going to immerse into the molten silicon has to be held in a very stable by a very stable system, unless and until you have the chain and pooling mechanism which is lifting the crystal, seed crystal at a defined or a precise rate. If any jerk can damage the orientation of the crystal. So, this particular feature is very important. The system should be very stable. The chunk and the rotation. Now, when you are lifting the silicon ingot or the seed crystal, you are at the same time rotating it, because unless and until you rotate it, this is going clockwise and this is going anti-clockwise, and unless and until we rotate it, there will not be uniform deposition, because it is getting solidified and slowly grown. If you do not have proper pull rate, what will happen is, or any negative pull rate will melt this seed crystal into the molten silicon. So, we do not want that to happen, and therefore, the pull rate is very important. The seed chunk which is holding the being held up by the chain pulley mechanism has to be very stable, very precise, and the orientation or the rotation mechanism also should exactly ensure that the central alignment of the seed wafer seed crystal exists throughout the process. Third and the most important thing is the ambient. Any gases which are whatever gases you are controlling for cooling or using for cooling or driving away the byproducts should be all inert. The entire system should be vacuumized and you should have minimum contamination. Whatever byproducts you want to drive away, the use of inert gas is encouraged for driving away those things also, and the purge tube through which the wafer or seed crystal is inserted and seed crystal is taken out also needs to be properly isolated from the furnace. And lastly, the entire control mechanism wherein you are having the stable crucible rotation, the crystal pooling mechanism, the crystal chain pulley mechanism which is lifting the crystal, simultaneously controlling the rotation of the crystal, all that mechanism should have minimum intervention of human being. All these mechanisms, all these processes, all this particular thing needs lot of precision, and therefore, it is essential to have complete microprocessor based or automated system which will take care of this particular mechanism. Now, I gave you the resemblance, it is just like your sugar candy getting produced from molten sugar. So, similarly, from molten silicon, this solid silicon is getting formed. Since the whatever orientation this seed crystal will have, same orientation crystal growth will happen, and the rate will be exactly, or rate has to be exactly controlled, and there goes the mathematics behind this crystal growth mechanism. Now, what is this mathematics? The figure again is making your concept clear. Here you are having the seed crystal, single crystal which is being, this is basically the seed crystal which is used as a for growing the silicon. This is the molten silicon which is held up in the crucible. This is the complete chamber which is holding the entire system. This is the susceptor which is rotating the crucible in the clockwise direction, this is rotated in the anti-clockwise. So, there should be opposite in the direction of rotation. Then you have something known as this has to be what you call stable, and you have uniform heating throughout the molten silicon, because every time whatever the diameter of the crystal this particular furnace is, throughout that surface you should have uniform heating happening within this molten silicon, so that the deposition is proper and the rate at which the deposition is happening has to be properly, precisely controlled. So, this is what is the original polycrystalline silicon and this is the final ingot, and within them or in between them the processes which are happening are being depicted over here, and those processes are molten seed is dipped into the molten silicon, it is lifted slowly, this is how the ingot is formed and this is the final ingot which is being formed over here. So, right from polycrystalline, okay. So, from polycrystalline you have developed, okay, you have gone for pure crystal, okay, pure single crystal, okay, single crystal silicon wafer you have gone for. So, this is what is single crystal silicon wafer. So, you have gone for monocrystalline. So, what is the mathematics going behind it, because you need to, as an engineer you must know what is happening into it, what exactly is the process. Now, this is the diagram which is indicating the crystal growth axis. Here you are having solid seed crystal and here you are having the molten silicon. The rate at which the growth is happening is given by this particular equation, where L is the latent heat of fusion, dm by dt is mass solidification rate. Since the temperature is one of the factor which is governing it, so we have something known as a temperature T, and KL and KS are basically the conductivities which are defined, okay, of the solid and liquid phases, which are, or the elements which are, these are the two conductivity phases which are being shown. This equation is important because this is going to define the rate at which the growth has to happen and what is the maximum rate of growth that can be attained, and this under zero thermal gradient, when there is no difference of temperature, the maximum rate at which the growth can happen is, or the pool rate which is deciding factor in the growth of silicon, is given by equation Ks dt upon Ld into dx. So, this is what is the final expression which is explaining you or which is giving you the idea about, that is the latent heat of fusion, the rate at which the solidification is happening is a deciding factor in growth rate. Another mathematical analogy what you need to study to control the growth rate is basically given by equilibrium distribution or segregation coefficient. Now, this segregation coefficient is defined based on the two factors, that is Cs and Cl. Now, what are these Cl and Cs? These are basically the solubilities you can say, or these are basically the concentrations of solute and in the solid and liquid phases respectively. As you know, the molten silicon is having impurities into it. As the silicon growth is going to happen, or it is going to, crystal is going to grow slowly, the crystal will be in pure form and the concentration of impurity in the crystal is going to exceed slowly as the growth is happening. That means, when my crystal growth is happening, when my crystal is going to grow or when my crystal is completely formed, I need to know when am I supposed to stop. That means, this growth till what point of time I need to grow, till what point of time I need to stop this particular growing process, and that is being defined by this particular equation, and this equation is giving you the clarity about it. So, therefore, you need to know the equilibrium distribution or segregation coefficient. Now, this coefficient is deciding the ratio, or it is the ratio of liquid phase solvents, whatever concentration of solute which is available in the solids, and concentration of solutes available in the liquid phase. This ratio is always typically less than 0, because dopants, as the silicon is solidifying, the dopants or the impurities are rejected, and they are more and more impurities are basically getting, or the concentration of impurity in the molten silicon is increasing as the crystal growth process happens, except for oxygen and carbon many times. This is for some applications, you try to keep it this one. As the crystal grows, I told you the molten silicon is enriched with impurities, and you need to know, that means in first when the process starts, you will have pure crystal. As the growth process happens for a time interval t, your impurity addition into the single crystal will keep on increasing as the crystal grows, and therefore, the maximum, this is the final point you need to know, that is the normal freezing relation, and this freezing relation defines till what depth or till what rate you need to grow the crystal, and what is the concentration increase or rate at which the concentration is increased into the molten silicon. And therefore, this is basically x, this particular is the distance or the what you call distance for which the crystal is grown, and this distance for which the crystal is to be grown is essential component in the growth process. You have to remember that the growth, negative growth indicates the seed getting molten into the molten silicon, or basically you are having the reverse process. So, growth is happening because the seed crystal or the solidification of silicon and the seed crystal is increased, and therefore, we call it as growth and not the okay. So, this is how the similar orientation of the seed, this is happening, and therefore, this particular equation gives you the idea up to which you need to continue the crystal growth process, because when the impurity increases you need to stop, because that silicon ingot is of no use, and therefore, this freezing relation is important to check out what is the growth rate or how much crystal can be grown from the amount of molten silicon kept in the crucible. So, this equation is basically K 0 into C 0 into 1 minus x raised to the power K 0 minus 1. Now, this K 0 is nothing but the ratio of impurities in the solid and liquid, and therefore, the ratio is equally important, which is deciding the growth of silicon into from or growth of the silicon ingot from the molten silicon. So, here I told you already, C 0 is the initial melt concentration, C s is the solid concentration, and K 0 is the segregation coefficient, what we have studied already. So, this mathematics is basically giving you the idea, the rate at which the silicon wafer or silicon ingot can be grown from with the help of seed crystal from the molten silicon, and within the molten silicon the ratio of impurities in the solid and in the liquid decides the segregation coefficient. So, that ratio is also very important. Along with it the maximum pull rate is also important, what we have seen in the earlier equation. So, this all factors will decide the amount of ingot or the what you call height of the ingot which is getting formed, as well as the diameter of the ingot which is getting formed. Another process in this crystal growth is the localized heating process, and which is known as float zone crystal growth process. Now, instead of crucible, in this process we are having RF electrodes which are heating the polycrystalline ingot which into this polycrystalline ingot, and this polycrystalline ingot is locally heated basically. Now, locally you are creating a molten area, and from that molten area you are developing or you are touching the seed crystal to that molten area, and this again pull rate and the segregation coefficient and other factors will come into picture, and same thing will be done, but rather than holding the molten silicon into the crucible, we are heating it locally, and from that local heating area or from that particular area we are growing the seed. Now, what is the difference between, now here also you are having the inert gas which is being flown to drive the byproduct, the molten zone is confined, you do not have any crucible to hold this particular molten silicon. ingot is the same, like seed crystal is of same orientation, or it is basically the product which is deciding the growth rate. Apart from the localization in the heating, like localization process used for the heating the silicon or melting the silicon, most of the other parameters or mathematical analogies are almost same. Only thing is, here since the crucible is not being used, there has to be a lot of precision involved in pulling the seed crystal, because the area is confined. The difference, the main difference between the float zone and the normal processes, there is, since the area is limited, the crystal which is being formed is of high purity, and the application of such crystals or the wafers which are fabricated or which are prepared from such kind of float zone methods are used, or they find their applications in power devices and precision detector applications. It is high transparent, okay. It is highly transparent to terahertz radiation, and is often used for fabrication or fabricate the optical components such as lenses and windows, for operating them in the terahertz range. It is also used, such particular wafers are also used for solar arrays and high efficiency, energy efficiency applications. The important difference is, again, here in FZ process, as I told you, there is no crucible involved, and therefore, the impurities which are dissolved in the molten silicon are, there is no such question arising, and therefore, temperature gradient and corresponding variations in the concentration, those problems are free, like you are not facing those problems. But there is lot of precision involved, because there is localized heating, the pool rate and the precise control on the seed crystal holding contact area, that is what we have seen, the solar area which is decided by the segregation coefficient, and the contact area which is being decided, like the interface between the solidification and molten silicon, like solid seed crystal and the molten silicon are coming in contact. That area has to be very precise, there has to be uniformity in contact surface, and the rate at which the solidification is happening will precisely defining will be defining the crystal pooling rate or seed crystal pooling rate. Since there is minimum area coming in contact, any minutest instability or any minutest variation in the temperature gradient or any minutest variation in the contact surface can create elasticity and damage the crystal orientation, or damage the, or create whatever seed crystal is, the deposition can get hampered, and thereby impact the nature or the quality of crystal which is being grown. So, rather than monocrystalline, you will have something deformities or dislocations or some impurities, point impurities, surface impurities getting incorporated in the growth process. So, you have to be very careful in pool rate and the contact getting established between the seed crystal and the localized molten silicon area. So, before we end, let us summarize by answering the following questions. The first question, what you should be able to answer, is the preparation of metal grade silicon, which is prepared from the sand. Second, you should be able to describe how the metal grade silicon transformation takes place into electron grade silicon by pulverization process, or bringing in contact with the anhydrous hydrogen, or you have something known as CVD process. Then thirdly, and the most important part of this lecture or this particular topic, is the growth process happening through CZ process, in which all the 4 components, that is furnace, pull rate, the entire ambient temperature and the microprocessor based system which is controlling the entire process happening within that CZ growth process, has to be clearly remembered along with the schematic of the CZ furnace. Then what is happening in the FZ process and the difference between CZ and FZ crystal growth processes. If you can answer all these questions, describe CZ process and FZ process completely, you are ready to go further into the process of wafer preparation that we are going to study in the third lecture. So, thank you, good luck and God bless.